Welcome. And we have a guest from Kyoto University, Japan. He's a graduate student of Kyoto University. We are at the BC several. And he's a collaborator of mine. He has worked on like stellar players, especially like from X-ray data and multi-frequency data set. And also he's a member of the XRISM team, which is a new X-ray satellite used for various objects. He's also in the instrument team. And he talked about fine emissions, especially like iron care burn. I hope, I think, will come.
Thank you for introduction and giving me an opportunity to have a presentation today. I'm Shun Inoue coming from Kyoto University in Japan. And I'm coming to US this and next week to attend an AGU annual meeting in New Orleans. Today, with this title, I'm going to talk about our three latest research results about stellar flares mainly in X-ray. First, let me briefly introduce myself. I'm a PhD fourth year student at Kyoto University in Japan. And my supervisor name is Teruaki Enoto. He is an X-ray astronomer and he has been participating in many X-ray satellite missions such as SUZAC, NICER, and XRISM. And I'm likely to get my PhD degree on March 2027. And these are my research keywords. I have been researching stellar magnetic activities such as stellar flares and coronal mass ejections on magnetically active binaries, RS type stars, and also on Fleming sequence stars such as protostars and T-tauri stars in some star-forming regions. Also, I have been a calibration and detector team members of Japanese new X-ray satellite XRISM. XRISM was launched on 2 years ago, and I have been calibrating the effective area and quantum efficiency of X-ray CCD camera on board XRISM. But today, in this presentation, I focus only on these scientific topics and don't mention my calibration works. As I said, my main research topic is solar and stellar flares. Solar and stellar flares are explosive phenomena wherein the magnetic energy stored around spots is suddenly released through magnetic reconnection. And this is an imaginary picture of large super flares on the K-type star of the RS-type binaries. RS-type binary is a very famous magnetically active binaries consisting of K-type giant and G-type main sequence stars. And the energy scale of stellar flares on RS-type stars is much larger than the largest solar flares. And such large flares also occur on Fleming sequence stars, such as class 0-1 protostars and class 2 to 3 T-tauri stars. And in the case of Fleming sequence stars, intense flare-driven X-ray emission from the central star can influence planetary formation and the environment of exoplanets. Particularly, I'm interested in the X-ray observational study of stellar flares with the iron K-alpha line. This is a X-ray spectrum of the stellar flare on the RS type star IIP. You can see a clear 3 iron lines in this energy band. The iron K-alpha line at 6.4 kilo electron volt, and iron 25 helium alpha line at 6.7, and iron 26 lime alpha line at 6.9 keV. And these iron 25 and 26 lines are very high temperature lines, and they arise from highly ionized iron ions in a high temperature thermal plasma in a flare loop. And on the other hand, the iron K-alpha line at 6.4 keV has been considered to be emitted from the photosphere because this line originates from neutral or low ionized iron ions, and such iron ions cannot exist in the corona because the temperature of corona is too high to keep such low ionized iron ions. And therefore, this line has been considered to be emitted from the photosphere. So we can say that this line is very unique because even though the line is emitted from the photosphere, but observed in X-ray wavelengths. And the iron caliber line is emitted when the K-shell electrons of the neutral and low ionized iron ions in the photosphere are ionized. And there are two possible mechanisms of the ionization. The first one is photoionization. Photoionization means that ionization by hard X-ray photons from the Fourier loop. And the second candidate is a collisional ionization, which means ionization by non-thermal electrons accelerated in the Fourier loop. So actually, it remains unknown which of these emission ionization mechanisms is dominant for the iron caliber line during both solar and stellar flares. The main reason why this issue is unresolved is a lack of observation of iron caliber observation during both solar and stellar flares. And this histogram shows a history of iron caliber observations during solar and stellar flares. As you can see, the iron caliber lines of solar flares are frequently observed in 1980s by Hinotori and solar maximum emission. And at that time, the frequent observation of the iron caliber line of solar flares with Hinotori and solar maximum emission triggered active debates on the emission mechanism of the iron caliber line, but no clear conclusion was reached at that time. And after that, after the solar maximum emission, the solar iron caliber line of solar flares has not been observed for more than 30 years since 1989, because there are no X-ray satellites which can conduct X-ray spectroscopic observation in this energy band for the sun. On the other hand, stellar observations with SWIFT and NICER have gradually increased the number of iron caliber line detections during stellar flares in recent years. Anyway, because the iron caliber line has not been observed for more than 30 years for the sun, the emission mechanism of the iron caliber line has become a forgotten and unresolved problem. The biggest motivation to identify the emission mechanism of the iron caliber line is its potential usefulness as a geometrically diagnostic tool. If the photoionization is the origin of the iron caliber line, we can estimate the Fourier loop height and the Fourier loop inclination angle between the observer and the Fourier loop. By combining the observation of the iron caliber line and 3D radiative transfer calculations. Because the fluorescence efficiency of the iron caliber line has the dependency on the Fourier loop height and the inclination angle between the observer and the Fourier loop. If we can determine the Fourier loop latitude for stellar flares, we can discuss whether each flare directly hit the exoplanets or not. Therefore, identifying the emission mechanism of the iron caliber line is essential for using this very useful line as a geometric diagnostic tool. With this background, in this presentation, I will present three latest research results about iron caliber lines. The first one is a result of our systematic study of the iron caliber line on RS CVn-type stars using NICER archive data. Systematically analyzing NICER archive data, we increased the sample size of the iron caliber line during stellar flares and detected a positive correlation which supports photoionization. And this work is already published by monthly notice on last August. And the second topic is our simulator results of our simultaneous 5B and X-ray observations over large super flare on the RS CVn-type star UXRE. Actually, this work was accepted by APJS three days ago, and now you can find the preprint version in the archive server. And in this work, we use NICER, X-ray telescope NICER, and Japanese UV satellite Hisaki, and conducted simultaneous 5 and X-ray observation. And as a result, we found more clear evidence of the photoionization origin of the iron Kepler line. And the last topic is our recent observational results of the class 1 protostar area 29 with Japanese new X-ray satellite XRISM. In this study, with XRISM high energy resolution spectroscopy, we detected both neutral and low ionized iron Kepler lines, and we will discuss the X-ray penetration depth in the protoplanetary disk using these iron Kepler lines. So the first two topics is about the emission mechanism of the iron Kepler line, and the last topic is an applied study in which we use the iron Kepler line as a diagnostic tool. So this is today's contents. So first, let me start with our systematic study of the iron Kepler line on Earth metal stars. The target stars in this study is Earth-type binaries. As I said, Earth-type stars are very famous magnetically active binaries consisting of K-type giant and G-type main sequence stars. And they are so magnetically active that many large superflares from Earth-type stars have been observed by X-ray telescope NICER. NICER is an X-ray telescope on board ISS, and it has been operated since 2017 and has very large effective area. However, there are no reports of iron Kepler lines of Earth-type stellar flares obtained by NICER, observed by NICER. Therefore, we consider that there are many unreported iron Kepler samples in the NICER stellar flare archive data. Therefore, then we analyzed all Earth-type stellar flare data obtained by NICER since 2017 and searched the iron Kepler line by fitting the line with Gaussian. And this is an example of a flare during which the iron Kepler line was detected. The left panel shows the right curve of the flare. You can see the very clear initial phase of the flare. And we extracted the X-ray spectrum using the data during which the initial phase of the flare. And the right figure shows the X-ray spectrum of the flare obtained by NICER. You can see a very clear iron Kepler line at 6.4 kb with 25 and 26 lines. And we fit this iron Kepler line with Gaussian, and as a criteria, when a line center energy comes in the 6.4 to 6.7 kilo electron volt with a 90% lower limit of normalization exceeding 0, we think that the iron Kepler line is detected in the spectrum. And with this criteria, finally, we found 25 new iron Kepler samples in the NICER stellar flare archive data. And using these new detected samples, we can discuss the emission mechanism of the iron Kepler line. This figure shows the relationship between the iron Kepler line luminosity and the hard X-ray luminosity from a thermal plasma in a flare loop. And these four crosses are previous works obtained by Swift. And these squares are new samples detected in this study. And you can see very clear positive correlation between the iron Kepler line luminosity and hard X-ray luminosity with its power law index of 0.86. And this positive correlation supports the photoionization scenario of the iron Kepler line because in that scenario, the iron Kepler line is emitted when the K-shell electron is ionized by the hard X-ray photons. Therefore, the iron Kepler line luminosity should be correlated with hard X-ray luminosity as shown in this equation. F alpha means iron alpha flux, and this this term corresponds to the hard X-ray luminosity. By increasing the sample size of here, okay,
Can I ask?
yeah, okay.
So when I look at this plot, if I exclude the 3 data points on the left,
Yeah.
it looks like a linear in this low level scale.
Yeah. It's a very important point. Yeah, we also these 3 data points are relatively strange because the K-alpha line luminosity is higher than we expected, as shown in this purple shaded area, and we think that for these 3 cases, the collisional ionization may also contribute to the iron alpha line emission.
Sorry, so that means there could be actually a plateau then a hollow, or they are actually outliers and
For the lower energy range, it may be plateau, but we cannot determine this because it is difficult to observe in such lower energy range. Yeah.
So I had a question about that too. It sounds like you may have answered it, that this was probably an observational bias, because if their ones are consistent with the rest of the line, you wouldn't have been able to observe them.
Yeah, we also think that there is a possibility of, as you said, and we only say that this is consistent with the photoionization, but cannot strongly support photoionization, but it is consistent with. Thank you. And my first topic. And in the next topic, I can show the more clear evidence of the photoionization scenario. The second topic is our simultaneous phi UV and X observations of a large super flare on the Arctic method UXR. This is a light curve of the flare highlighted in this study. The upper panel shows the X-ray and the lower panel shows the phi UV light curves. X observations are conducted with NICER, and phi UV observation was conducted with Japanese UV satellite Hisaki. Hisaki is originally designed to observe planets in solar system, in our solar system, such as Jupiter, but it can also be used to observe some stellar targets, and this is the first result of Hisaki for stellar targets. And this flare was so large that the energy of 10 to 36 ERG was released in both X-ray and phi UV bands. And also, you can see very clear new part effect between X-ray and phi UV. This blue shaded area shows the phi UV flare peak, and the red shaded area shows the X-ray flare peak. As you can see, the phi UV flare peak is about 1.4 hours earlier than X-ray flare peak, which can be explained as new part effect. Let me briefly add the context of new part effect between phi UV and X-ray in this slide. As I said, phi UV flare peak tends to be earlier than X-ray flare peak in both solar and stellar flares, and it can be explained by new part effect, which means when a solar and stellar flare occurs, at first, non-thermal electrons accelerated by magnetic reconnection travel from reconnection point to the downward along the magnetic loop in the corona. And at first, the non-thermal electrons are injected in the transition region, and they hit the plasma in transition region, and after that, they hit the chromospheric plasma. And finally, the heated chromospheric plasma evaporates into the flare loop in the corona with soft X-ray emission. Therefore, the phi UV flare peak becomes earlier than soft X-ray flare peak, and the most important point here is that the soft X-rays originate from hot thermal plasma, and therefore it can be said thermal emission, but the phi UV emission traces heating of the transition region by non-thermal electron. Therefore, phi UV emission can be a proof of the non-thermal emission. So X-ray is a thermal and phi UV is non-thermal is an important point here. Let me return to our observation. This is the X-ray spectrum of a flare over stellar flare during on the R scan metapital UXRE obtained by NICER. And we fitted the X-ray continuum with 3 temperature CIE. CIE means the collisional ionization equilibrium plasma model. And we estimated the Fourier temperature is about 18.3 megakelvin, and the Fourier loop size is about 0.2 to 3.9 solar radius. And we can say that this flare is much hotter and larger than the largest solar flare. And furthermore, we detected an iron Kelvin line during this flare, this purple line. And the equivalent width of the iron Kelvin line during this flare was about 17 electron volt. The most important detections in this study is the time variation of the iron Kelvin line during this flare. This figure shows the right curve of the iron K-alpha line and iron 25 Helm alpha and iron 26 Lime alpha line luminosity during this flare. And the blue shaded area shows the non-thermal 5D flare peak, and the red shaded area shows the thermal X-ray flare peak. And as you can see, the iron K-alpha line luminosity peak coincide with thermal X-ray flare peak, not with non-thermal 5D flare peak. This strongly supports photoionization scenario of the iron K-alpha line, because if the iron K-alpha line is emitted as a result of collision by non-thermal electrons, the iron K-alpha line peak should be coincide with non-thermal 5D flare peak, but in this observation, we detected the coincidence of the iron K-alpha line and thermal X-ray flare peak. We think that this is the strongest clear evidence of the photoionization origin of the iron K-alpha line. And finally, we also conducted a 3D radiative transfer calculations to test the validity of the photoionization scenario and demonstrate the potential of the iron K-alpha line as a geometrically diagnostic tool. The left figure shows our calculation setup. We treated the Fourier emission as a point and spherical emission source, and we varied the inclination angle between Fourier loop and observer from 0 to 19 degrees. And the right figure shows right figure compares our calculation results and observed equivalent width of the iron K-alpha line. The vertical axis shows the equivalent width of the iron K-alpha line, and the horizontal axis shows the inclination angle between the observer and Fourier loop. And as shown in this figure, the observed equivalent width of the iron K-alpha line can be explained by our calculations assuming photoionization. And furthermore, we also demonstrate that the potential of the iron K-alpha line to constrain the Fourier loop size and latitude. For example, in the case of the Fourier loop size is 2 solar in this orange line, the inclination angle of the Fourier loop between the Fourier loop and observer should be constrained from 30 to 17 degrees. So from this result, we think that the iron K-alpha line is very useful as a geometrical diagnostic tool for spatially unresolved stellar flare loops. And this is our second result. And from the first systematic result and the second multi-beam approaches, we can conclude that the emission mechanism of the iron K-alpha line during stellar flares is dominated by photoionization.
If the inclination angle,
Hmm?
if the loop is bigger, the emission height is higher,
Yeah.
then if the irradiation is bigger, then equipment is larger.
No, when the loop size is bigger, the flux of the X-ray flux of the X-ray flux of the photosphere is becoming decreased because therefore the equivalent width become decreased.
Wait, what? Why is that? Why does the photosphere flux decrease with the bigger loop size?
Because the distance between the loop height and the photosphere is is bigger, the flux, X-ray flux at the photosphere comes from the rooftop becoming degrees, and therefore fluorescent efficiency becoming lower and lower, and the equivalent width of the iron Kelvin line becoming smaller and smaller. Yeah, it is important point. Thank you. And this is our second result. And the last topic is our recent observation result of the protostar area 29 with XRISM. The first and second topic dealt with RS CVn-type binaries. In other words, late-type stars, but for the last topic, we observed the protostar area 29. And Primary sequence stars such as protostars and T-tail stars also show the magnetic activity such as flares. And unlike late-type star cases, the magnetic activity of protostars or primary sequence stars can have an effect on the planetary formation around the central star. Particularly, X-ray emission from the corona of the protostar or T-tail stars can destroy molecules such as water and organics in the protoplanetary disk. This process is very important for disk ionization, accretion, and furthermore, the emergence of life in the system. This is a newly emerging field known as X-ray-induced chemistry, which has becoming more and more important in the planetary formation studies. And chemical calculation is actively conducted in the X-ray-induced chemistry, but the observational studies of X-ray-induced chemistry is still limited. And by the way, the iron Kelvin line has also been observed on primary sequencers. This figure shows the X-ray spectrum of the protostar obtained by Chandler. And you can see very clear iron Kelvin line at 6.4 keV. And in the primary sequencer cases, this line has been considered to be emitted as a result of photoionization of the protoplanetary disk by coronal X-rays from the central star. And therefore, the iron Kelvin line can be a tracer of the ionization process of the protoplanetary disk by coronal X-rays from the central star. And one important parameter of the iron Kelvin line is its line center energy. This figure shows the relationship between the iron Kelvin line center energies and the ionization parameter of the photoionized plasma. Ionization parameter is defined as this equation. Lx means the X-ray luminosity of the central star, and N is the disk density of the protoplanetary disk, and R is the distance between the protostar and the line emitting region. And as you can see, the line center energy of the iron Kelvin line strongly depends on the ionization parameter. And therefore, if we can measure the line center energy of the iron Kelvin line accurately, we can estimate the X-ray penetration depth in the protoplanetary disk. This parameter is very important for X-ray-induced chemistry because the amount of water and organic molecules which is destroyed by X-rays depends on this X-ray penetration depth. But however, previous X-ray satellites such as XM Newton, Chandler, NICER, Swift cannot measure the line center energy of the iron Kelvin line accurately because they didn't have enough energy resolution. For example, this right figure shows the X-ray spectrum of the protostar obtained by XM Newton. XM Newton could detect the iron Kelvin line, but it could not determine the iron Kelvin line center energy accurately because, as you can see, the energy resolution of XM Newton was not enough for determining the iron Kelvin line center energy. Here, let me introduce the Japanese new X-ray satellite XRISM. XRISM was launched 2 years ago, and it has two instruments, microcalorimeter resolve and CCD camera extent. Using a microcalorimeter resolve, we can conduct high-resolution spectroscopy in the 1.7 to 12 kiloelectron volt. The energy resolution of resolve is much better than previous X-ray satellites such as Newton and Chandra. And furthermore, using X-ray CCD camera extend, we can conduct wide field X-ray imaging observation in the 0.4 to 13 kiloelectron volt. The field of view, FOV of extend is wider than any other previous X-ray satellites such as Chandra and Newton. And in this study, we observed the class 1 protostar area 29 using the XRISM. Area 29 is located at the low Ophiuchus star-forming region. This is an extended image of the low Ophiuchus star-forming region, and this green circle shows our main target, area 29. And as you can see, there are many other pre-main sequencers around area 29. But the microcalorimeter resolve can observe only areas 29 because the FOB of resolve is much narrower than extent. And this is a high resolution spectrum of areas 29 obtained by resolve. You can see the fine structure of the iron 25 helimalpha line at 6.7 kb, and we also found the neutral iron alpha line at 6.4 kb. And furthermore, we also detected low ionized and mildly ionized iron alpha lines. And this is the first time that both neutral and low ionized iron alpha lines have been separately detected due to high energy resolution of resolve. And we think that each of these lines originate from different regions in the protoplanetary disk, and we can discuss X-ray penetration depth in the disk using these lines. Then, as a next step, now we are conducting 3D radiative transfer calculations to determine the emitting region of each of neutral and low ionized iron alpha lines observed by resolve. And in our calculation, we assume the standard protoplanetary disk density distribution, and use extend wideband spectrum using as an input SED. And now we are running a radiative transfer calculation, and please look forward to upcoming our simulation results in the future paper. This is my third topic. Let me summarize. In this presentation, I presented about the three latest research results about the iron alpha line during stellar flares. And we have concluded that the emission mechanism of the iron alpha line is dominated by photoionization by our systematic and multi-wavelength approaches. And also, as an applied study, we also observed the protostar area 29 with XRISM and detected both neutral and low ionized iron alpha line with its high energy resolution. And the most important message of my presentation is identifying photoionization as the iron alpha line emission mechanism. Now we can use this useful line as a tool for proving geometry for stellar flare loops and disk ionization process for the protoplanetary disk. This is my message of this presentation. And okay, that's all. Thank you. Any question?
My first question
Yes.
is about the ability to screen geometry.
Uh-huh.
While we're doing this for RS CVns and other stars, are you able to do this for M-dwarf flare stars as well? Because we have a huge debate about whether young M-dwarfs magnetic fields are great in such that flares directly impact the planets or cut off.
Yeah. Basically, it also can be used for M-dwarf, but it is difficult to observe the iron alpha line on M dwarf because the photon statistic of X-ray spectrum is essential to detect to observe the iron alpha line, and the flares of M dwarf is relatively the photon statistic is worse than R CVn-type binaries.
That's the follow-up question.
Yeah.
I was assuming that it was probably due to the photon statistics, and so if that's the case, could you maybe stack large numbers of network players?
Yeah, yeah,
to make that claim?
I think that it is one of the strategy, and if you stack and the photon statistics become better and better, we can discuss same geometrically estimation as shown as same as R CVn-type binaries, I think.
Some proposed principle in physics. There is a cycle and it was rejected, so I'm sure. Yeah, some comments. You did right.
Right.
Yeah.
Yeah, thank you.
Thank you.
Great talk. Can I also ask about the geometry here? How is there a way that you can break the degeneracy between the inclination and the height? Because it seems like
Yeah. As you can see in this figure, as you said, there's a degeneracy between the inclination angle loop heads. For example, this blue line shows a loop size 1 solar, 2 solar, 3 solar, and for example, the inclination angle is 14. Both loop size 2 solar and 3 solar has a solution for the observed equivalent width of the K alpha line. So the important point is measuring the iron K alpha line equivalent width accurately. So making error range smaller is essential to accurately estimate the geometry of stellar flare loop, and for that purpose, the XRISM is very nice because the energy resolution of XRISM is much better than this is a nicer result. And if in our future XRISM observation, we can make the error range much smaller and more accurately determine the loop both loop size and inclination angle, I think.
Clear some frequency, right? A bit difficult to prove for viewers because observing that is very
Thank you.
Just to understand better what you just said, but even if the error range is, let's say, 0,
Yeah.
so it's just a line.
Yeah.
You still have degeneration.
Yeah. We cannot completely remove the degeneracy. Yeah, but yeah. So yeah, as you said, yeah, you are correct.
So you need some other observations.
Yeah, but we also estimate the loop size from the emission measure and the temperature of the which can be estimated from the X-ray continuum shape, and using temperature and emission measure, we can roughly estimate the loop size. So loop size is determined by from temperature and emission measure, and combining the loop size under this method, we can remove degeneracy, I think.
Okay. Image browser.
Here's some papers by Rachel Austin about that.
Yeah.
You know.
This might be.
The power is combining the two.
Yeah, combining is important.
You're planning to for other gaps. You said protein plus one.
Yeah. I'm also interested in the X-ray observation of class 2 theta, class 2 or class 3 theta results are relatively more evolved because that phase is also important for planetary formation. And now I'm planning to submit a new proposal for XRISM to observe the class 2 theta disturbance.
Can you also go back to the slide where you were showing the resolution of GIFM compared to
This one?
maybe Chandra? I was wondering about the high energy grading on Chandra. I know can reach up to around
Yeah.
1,000 in R.
Uh,
How that would compare.
Yeah, the energy resolution is different between Chandra high grading and the XRISM. Chandra grading, for the Chandra grading, the energy resolution in soft X-ray below 2 kilo electron volt is much better than resolve. But for the Chandra doesn't have enough energy resolution for iron alpha band at 6 point, around 6 kb. For the around iron alpha line energy range, the microcomputer resolve is about 10 times better than Chandra grading.
Thank you.
Thank you very much. So there it's not correct. Yeah, for the soft X-ray. Yeah, this is a spectrum of maybe CAS-A, CAS supernova remnant, and the energy resolution around iron of resolve is much better than previous X-ray satellites. It is correct. Thank you. Any other question?
No more questions, thinkers.
No? Thank you. Thank you.
So much.
Thank you.
That was really interesting.
Yeah.